Hello, this is Professor Mark. I'm going to talk to you about Chapter 10, the last chapter for SEC 201, General Chemistry 1. So characteristics of a gas, there are three forms: solid, liquid, and gas. If we take the example of water, in its solid form of ice, it has a shape um, and a definite volume. If we switch to the liquid, when it goes from ice to liquid water, it will take the form of whatever container it's in, whether it's the ocean, whether it's a cup, whether it's a bathtub. There is a definite volume that you can measure. And when it goes to steam or a gas form, there is no specific shape or defined volume. And you can tell going from solid liquid to gas, the molecules of H2O go further and further apart from each other from solid to gas, less structure. So I just mentioned gases don't have a fixed shape or volume. They can be easily compressed. They have lots of empty space in between the molecules, and they move freely among others molecules. You think of air as a homogeneous mixture, which is made up of things such as 70%, approximately 70% N2, about 20% O2, and some other gases like CO2 and H2O, etc. And gases have a lower density, of course. If they had a high density, for instance, if they're higher than water, you'd have the reverse. You'd have air underneath water, which is not the case. And they're mainly found on the right side of the periodic table. A lot of nonmetals are in the gas form. So here we can measure the gas in terms of pressure, which is the force divided by area. The unit that we will use mostly is atmospheres, 1 atm. However, the SI unit is Pascal, which is also a Newton divided by meter squared. But as I said, we'll focus on the atmosphere, which is also equal to 760 millimeters of mercury and 760 torr. So here we have a gravitational force, the pressure exerted on the surface, at the surface of the Earth is 1 atm. So a barometer is a device that measures the pressure of the room or the environment that you're in. And as I said earlier, we have 1 atmosphere is equal to 760 millimeters of mercury. How is this shown? If we had a container full of mercury and we put a tube, over this container of mercury, the atmospheric pressure, which pushes down on this mercury, would cause the height here, would cause the mercury to go up this tube and have a height of 760 millimeters of mercury. And this is at 1 atmosphere, sea level. So that's why we came up with the unit of 1 atm is equivalent to 760 millimeters of mercury and 760 torr. We also use mercury also before in thermometers, if you remember, to measure temperature, and as well. And we use mercury in barometers because also for convenience, as you guys know, at room temperature, mercury is in the form of a liquid. Its density is about 13 times greater than water. So the same measurement, if we're done, would be about 13 times greater than 760 millimeters of mercury to get the same pressure for 1 atm for water. Also, mercury can withstand larger temperature changes. If you know, for water at 100 degrees, it starts to turn from liquid to gas. Therefore, it would start to evaporate this liquid. So we use mercury for this barometer. In experiments, we use this device called a manometer, and it can measure the pressure of a gas vessel. So if there's an experiment where a gas was released, it can measure how strong that gas is in terms of pressure by how far the mercury moves in the manometer. So a question here is, what is 475 torr expressed in ATM? So again, if we remember our unit conversions, you can pause the video and try on your own. But the unit conversion, you write 475 torr. The unit conversion, 1 ATM on top, 760 torr on the bottom, 760 torr on the bottom. And the units would cancel, torr on the top, torr on the bottom. You're left with ATM. So 475 divided by 760 would give us 0.625 ATM. The second one, again, is hopefully a straightforward calculation. The pressure of a tire is measured as 2 ATM. What is the pressure in millimeters of mercury? It would be 2 ATM times 1 ATM on the bottom and 760 is the conversion factor, millimeters of mercury, cross, and when you do 2 times 760 you get 1520 millimeters of mercury. So in a closed container, as the temperature increases, more gas vapors form. So in this case, we would have a closed container. If we heated up the closed container from, let's say, underneath, so if you're boiling water and you covered the pot with the lid, that would be a closed system. The vapor above a liquid accumulates, and then it creates pressure we call this vapor pressure. Similarly, in an open system, in this case, we have here a beaker of water. We have a pressure of 760 millimeters of mercury pushing down on the water, and below we're heating it up. Okay, so if you heat up the water molecules, they move faster. Eventually, the water reaches its boiling point. And this is also when the vapor pressure becomes equal to the atmospheric pressure, and then bubbles will start to form at the bottom. When you boil water, the bubbles start to form at the bottom, and they want to push up and go to the surface. This is how we start to see water boiling. So the question for you, if you're on Mount Everest and you want to boil some water, you will need a temperature lower or higher than 100 degrees Celsius. 100 degrees Celsius is the boiling temperature of water at 1 ATM. First, we have to establish, when you're on Mount Everest, is that a higher pressure or lower pressure than that at sea level? And it's a lower pressure. It's harder to breathe on Mount Everest. So it's a lower pressure, less oxygen on Mount Everest. So which correlates to a lower temperature than 100 degrees to boil water, because there's less pressure pushing down on our liquid in this case. So to overcome this pressure, you would need to heat the water up less. So there are 4 characteristics of the gas that we want to be familiar with. One is pressure, and the unit we use is atmospheres, even though it's not the SI unit. For volume, it's liters. For temperature, it's Kelvin. And for the amount of gas molecules, we say moles. So just a short math lesson. We say here, if we have variables A and B with a constant K, if there is, we say, a direct relationship, meaning if B increases, A will increase, and if B decreases, A will decrease as well. We have the kind of, say, opposite relationship. We use Q and R in this case. So Q equals K divided by R, where K is a constant. We say Q and R are indirectly proportional to each other. So if Q increases, R will decrease, and vice versa. If R increases, Q will decrease. So we're going to look at 4 laws relating to, we call them gas laws. The first one is Boyles Law, which states that the pressure is inversely proportional to the volume, provided that the amount of gas stays the same and the temperature stays the same. Meaning that if we look at this photo here, the volume is 4 liters. We have decreased the volume, so we decreased the volume by 2 liters. What have we done? To decrease the volume, we increased the pressure of the container. So we increased from 1 atm to 2 atm. So this is an inverse relationship, meaning that if we decrease the volume, the pressure will increase. Boyles Law. And this works at a fixed amount of gas and at a constant temperature. So if we can write P is inversely proportional to 1 over V, it can be written as P equals K divided by V. So for this proportionality here, we can turn it into an equal sign by providing a constant. So if we had a situation, just like in the previous, if we had a balloon or a piston, if we had a situation where P1, V1, this balloon had a certain pressure and a certain volume, which equals to the constant. So just rearranging this equation here to here. So rearrange it, and P1 stands for the initial pressure, V1 is the initial volume, which equals to K. So if we were to squeeze down on this balloon, the pressure would increase and the volume would decrease. So this is just the situation of what happens after we change the conditions, but the concept would remain the same. So my question to you is, if P1 V1 equals to K and P2 V2 equals to K, does P1 V1 equal to P2 V2? And the answer is yes. So we can rewrite this equation as P1 V1 equals to P2 V2. It's the same amount of gas, and the temperature stays the same. So as I just said, P1 V1 equals P2 V2. Let's try to put this in our problem. If you take a look, we have just determined that a particular sample of ammonia gas has a volume of 0.0070 liters at a pressure of 1.68 atmospheres. Keeping the temperature and the amount of gas constant, we compress the sample to a volume of 0.0027 liters. What is its new pressure? So basically we're just trying to apply this equation. And we have all the variables. We have P1, which is the initial pressure. So we're taking a word problem and again trying to figure out the equation to use and its variables. The initial volume is 0.0070 liters. The final volume is 0.0027 liters. So without doing any calculations, we see here the volume has decreased. It's gone from 0.0070 to 0.0027. If the volume decreases, the pressure has to increase. So when you use this equation, you need to realize that your answer for pressure will be greater than 1.68. And when we plug in the values, we get a value of 4.4 atm. So you can just pause this and try this on your own. If you read the problem, a sample of nitrogen gas has a volume of 4.2 liters at 1 atm. If the pressure is increased to 0.075 atm with no change in temperature or amount of gas, what will the new volume be? well, I have written out the equation for you. V2 equals to P1 V1 divided by P2, and this comes from this original equation we derived. V1 equals to P1 V1 equals to P2 V2. So if we isolate V2, that's what we've done here. So we divide both sides by P2, and we just plug in our values. So P1 gain would be 1 ATM, 1 ATM. V1 would be 4.2 liters, and P2 would be 0.75 ATM. So the pressure went down from P1 to P2, so the volume should go up. And when you plug in the values, yes, it went to 5.6 liters. The next question, what is the new volume in liters of an 8.0 liter sample of Freon after its pressure is changed from 550 millimeters of Hg to 2200 millimeters of Hg at constant temperature? So we first have to convert this to ATM, and this comes out to 0.723 ATM. This is for P1. How did we do that? We did 550 divided by 760 millimeters of mercury. Again, I have attached the answers on the CUNY Common Blackboard. The next one, we need to convert 2200 millimeters of mercury to ATM, and that comes out to 2.89 ATM. Again, we did 2200 divided by 760, and our V1 is 8 liters. So when you plug in all the values into this equation here, we know 3 of the variables, so we can find the fourth one. We get 2.0 liters. And if the question was to the correct number of significant figures, this 8.0 is 2 significant figures, the lowest one. This is also 2 significant figures, and 2 significant figures, we get 2.0 liters. The second law is Charles' law, and it says the volume is directly proportional to the temperature. So if I took this is again at fixed amount of gas and constant pressure. So if I took a balloon and I put it in the freezer, the balloon will shrink. Okay, so as the temperature decreases, the volume will decrease. This is a direct proportionality relationship. So if we do the same idea, if we had V1 equals to, well, let's say V1 divided by T1 equals to K. So this is the initial situation. We freeze the balloon. The temperature, the volume will change. The temperature will change as well. If the temperature goes down, the volume will go down too. This is a direct relationship. And as a same idea with the Boyles Law, if both of these values equal to K, then they equal to each other as well. So as I just said, if we have an initial situation of a balloon, and then we did something to the balloon, and the situation changed, we will get this relationship of V1 T1 divided by T1 equals to V2 divided by T2. So let's try to apply this in a question. 3.0 liters of H2 gas at minus 15 degrees Celsius is allowed to warm to 27 degrees Celsius at constant pressure. What is the gas volume at 27 degrees Celsius? Recall you have to convert the Celsius to Kelvin, so that's what I did here. In these examples, I convert minus 15 degrees plus 273 is 258 Kelvin. and then 27 degrees Celsius plus 273 conversion to 300K, and then I plugged in the values for V1, for T2 and T1, and I got 3.5 liters as our new volume. Again, this only works at constant pressure and the amount of moles stays the same. So you guys can try this on your own and pause the video. The equation is already isolated for you. A gas has a volume of 3 liters at 10 degrees Celsius. What is the temperature of the gas if it expands to 6 liters, assuming constant pressure and amount of gas as well? So all the equation is isolated for you. Again, you use V1 divided by T1 equals V2 divided by T2, and you want to isolate T2. So V1 will equal 3 liters. T1 is 10 degrees plus 273 equals to 283 Kelvin. Remember, the third one is V2 equals to 60 liters. So I'll just show you V1 divided by T1 equals V2 divided by T2. If I want to isolate T2, I will cross multiply, and then I will get T2 V1 equals V2 T1. And then when I cross multiply, and now I want to isolate the T2, I divide both sides by V1. These will cancel, and I'm left with T2 equals to V2 times V1 divided by V1. When I do the math, I get 566 Kelvin. For the next example, a sample of neon gas has a volume of 3.1 liters and a temperature of 12 degrees Celsius. Find the new volume of the gas if the temperature rises to 32 degrees Celsius. You can pause and give it a try. V1 is 3.1 liters. T1 is 285 Kelvin. Again, I did 12 degrees plus 273, and T2, 32 degrees plus 273 equals to 305 Kelvin. So when I plug into the formula, if I want to isolate V2, it's going to be V1 T2 divided by T1, and I get 3.31 liters. We have something called the combined gas law, where we put we combine two of the variables, Boyles and Charles' law. And when we combine the two laws, if you recall, for Charles' law, V is directly proportional to temperature. For Boyles' law, V is indirectly proportional to pressure. When we combine the two, we get this equation called the combined gas law, where P1 V1 divided by T1 is equal to P2 V2 divided by T2. So let's just use as an example. A sample of gas occupies 225 milliliters. Right now you should convert that to liters at 2 atm and 373 Kelvin. So these three numbers are for the initial conditions, V1, P1, and T1. And you're asked, what is the new volume? So you need to know the new volume. You don't know, but you know the pressure of P2, convert from 320 torr to atm, and from T2 to which is 65 degrees Celsius to Kelvin plus 273 gives us 338. So we plug these in. We isolate V2 and we get 0.539 liters. So you can pause the video and give it a try on your own. It says here a sample, 0.180 liters. Sample of gas has a pressure of 0.800 atm at 29 degrees Celsius centigrade. So we convert that to Kelvin. It says at what temperature in Kelvin will the gas have a volume of 90 milliliters of volume and a pressure of 3.2 atm. So our initial volume is 0.180 liters, which is given in the question. Our initial pressure is 0.8 atm. And our initial temperature, 302.15 Kelvin. And our final volume, which is given in the question, is 0.090 liters. Have to convert the 90 mils to 0.090 liters, so you divide by 1,000. And our final pressure is 3.2 atm. And our goal is to find the final temperature. So we isolate again the T2, so we cross multiply and we get T2 equals to P2 V2 T1 divided by P1 V1, and when we plug in all the numbers, we get 604 Kelvin. Our third law is Avogadro's law. It's at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of gas present. So if we had a balloon, let's say we blow into the balloon, we're adding more moles of gas. What's going to happen to the volume? It's going to increase as well. So V is proportional to the amount of moles. It's a direct proportionality. So if V increases, the volume increases, the amount of moles increases. So here again, we want to change the proportionality to an equal sign. So we add the constant K. So V is equal to K times N, where K is a constant. So let's use this. And again, if we have initial conditions and a final condition, they both equal to K. Similarly to Boyles Law and Charles' Law, we have V1 divided by N1 equals to V2 divided by N2. So let's try the problem here. If 0.75 moles of helium gas occupies a volume of 1.5 liters, what volume will 1.2 moles of helium occupy at the same temperature and pressure? So we have all our conditions. 1.5 liters is the initial volume. 0.75 moles is the initial moles. 1.2 moles is the final moles. And we want the final volume. So as I just said, if the amount of moles increases, the volume should increase as well when you do the calculation. So we isolate our V2 and we plug in our variables and we get 2.4 liters, which increases from V1. So we also have this condition we call STP, standard temperature and pressure. So STP, at STP, the temperature is 273 Kelvin, and at standard pressure, it's 1 atm. So again, whenever you see the word STP, it has to be associated with a gas. The conditions are 273 Kelvin, which is 0 degrees Celsius, and 1 atm. So a sample of gas occupies 125 milliliters at STP. So the volume, V1, will be 0.125 liters. Again, divided by 1,000, 125 divided by 1,000. And P1 will be 1 ATM because it says STP. T1 will be 273 Kelvin. V2, so you have to convert 65 degrees Celsius to Kelvin. That comes out to, for V2, that's what we are trying to figure out, question mark. T2, we convert 65 degrees Celsius to Kelvin, so that will be 338. We have to add 273, and the pressure, P2, you have to convert from torr to atmosphere, so 320 divided by 760 is 0.421 ATM. So again, we plug in all the values to isolate V2. We use the combined gas law, P1 V1 divided by T1 is equal to P2 V2 divided by T2, and we want to isolate V2. So when we do that, we came up with 0.368 as our V2 value. So the molar volume of a gas at STP is always going to be 22.4 liters. When you have 1 mole of it, doesn't matter what kind of gas, whether it's helium, whether it's argon, whether it's nitrogen, oxygen. If you're at conditions of STP and you have 1 mole of the gas, the volume will be 22.4. So our conversion factor at STP, again, remember you have to be at standard temperature and pressure. When the temperature is 273 Kelvin and the pressure is 1 atmosphere, the unit conversion is 22.4 liters for every 1 mole, or 1 mole for every 22.4 liters. So the question here is, what is the volume occupied by 2.75 moles of N2 gas at STP? You have the moles, 2.75 moles. You want to find the volume of nitrogen gas at STP. You simply multiply by 22.4 liters. The moles will cancel, and you're left with the unit of liters on top. This is a bit not as straightforward. What is the volume at STP of 4 grams of CH4? So here we have 4 grams of CH4. We need to convert this to moles. If you recall from the earlier chapters, if you have the mass of a compound and you want to find the moles, you will divide by the molar mass. So I took 4 grams divided by 16 grams. Where did I get this from? I got this from the periodic table. The molar mass of carbon is 12. The molar mass of 4 hydrogens is 4 times 1. So 4 grams divided by 16 grams. And then the next step is to multiply by 22.4 because that is at STP again. So once you have the moles, so 4 divided by 16, let me just try this for you. So if I did 4 divided by 16, I got 0.25 moles. And then you multiply that by 22.4, you get 5.6 liters. So you can pause and try this next question. What volume of O2 gas is needed to completely react with 15 grams of aluminum at STP? So again, you're given the the grams of aluminum, 15 grams. You need to first convert this to moles. So remember from our map, you need to divide by the molar mass. Where did I get 26.98 from? I got it from the periodic table. And this comes out to 0.555 moles of aluminum. The next step is to use the balanced chemical equation to find the moles of O2, because that's what it's asking for. What is the volume of O2? So we would multiply by 3 moles of O2 on top and 4 moles of aluminum on the bottom, and this comes out to 0.416, and the unit would be moles of O2. So now we have the moles. Since we're at STP, we can do 0.416 moles times 22.4 liters over a mole of O2, and this will come out to 9.32, I believe, or 33 liters, which is what they're asking for in the question. So just showing here what will cancel out. So I'll just try to put this into perspective with the STP. And this question is, what mass of Fe will react with 5.5 liters of O2 at STP? So if we remember our roadmap, if we had moles in the middle, we had mass. If you recall from earlier chapters, if you want to go from moles to mass, you multiply by the molar mass. Again, you have to look at the periodic table. If you want to go from mass to moles, you divide by the molar mass. We also had here on the right side, if we had the amount of molecules or atoms, molecules or atoms, and we want to go from moles to molecules, we have to multiply by Avogadro's number, 6.62 times 10, 6.02 times 10 to the 23rd. Likewise, if we want to go from molecules to moles, we divide by Avogadro's number. We also talked about in the chapter about molarity, if we want to go from moles to concentration, or big M, if we want to go from moles to concentration, we divide by the volume. And if we want to go from concentration to moles, we multiply by volume. And then I just introduced this new topic of STP. So if we want the volume, this only works for a gas. From moles to volume, we multiply by 22.4, and we do the reverse. If we want to go from volume of a gas at STP, this only works at STP, we would divide by 22.4. So we can use that in this particular problem. So what mass of iron will react with 5.5 liters of O2? First step is to go from volume to moles, so 5.5. Our roadmap says we have to divide by 22.4. So we'll just, to keep our units, we will take a mole of O2, divide by 22.4, and here we get 0.245. Once we have the moles of O2, we want to find the moles of iron, so we have to use the ratio. So we take 0.245, multiply by 4/3, and that will give us 0.245 0.326 moles of iron. Now that we have our moles of iron, we want to find the mass of iron. So we have the moles, we want to find the mass. We have to multiply it by the molar mass of iron. So 0.326 multiplied by 55.85 grams per mole. That gives us 18.3 grams of iron. So it's just a brief summary. We have Boyles Law, which is volume, which is inversely proportional to pressure at constant temperature in moles. We have Charles' Law, which is V is directly proportional to temperature. If volume goes up, temperature goes up. For Avogadro's Law, if the volume goes up, the amount of moles will go up. And there was a fourth law that I didn't mention. It's called the Gay-Lussac. It states that if the temperature goes up, the pressure will go up as well. And this can be seen. This is at constant mole and at constant volume. So if I took a soda can, and I took it into the desert, and the desert is really hot, meaning the temperature will go up, the pressure will go up as well, and in theory, the soda can will explode. So that's called the Gay-Lussac law, where T is directly proportional to the pressure as well. So we'll stop there for part 1, and we'll talk later about ideal gas part 2. Thank you.